Hello. How's it going? I apologize in advance if my voice is disappearing. Oh man, it's been crazy few days. On Tuesday, I lectured for about 4 hours total. Yesterday, I had to record a bunch of videos. And today, I just had a 2-hour lecture. And I'm telling you, it's not easy. Lecturing for a long time in a row. Just trying to stay hydrated, trying to keep the throat okay. Anyway, enough about my problems. People have worse problems in the world. You're looking at assignment 2. That's what today's class is all about. It's going to be really exciting. And I've seen some comments out there in the Twitch chat from people maybe not in the course or some people in the course about how assignment 1 was kind of dry. And we didn't really do a lot, and we're going kind of slow, and, you know, that's about to change, okay? Oh, we got our first bot in the chat. Let me ban this guy. How do I ban? There you go. Perfect. All right. So, assignment 2. We are making this game. It is a Geometry Wars clone type game. I'm hitting W, A, S, and D to move my character, who is this red octagon around the map, or around the window, and I'm shooting with the left mouse button. And when I kill something, or when my bullet collides with something, it will destroy that thing, and then it will spawn into miniature versions of itself. Those miniature versions will each will each have so we'll spawn as many of them as the original object had sides. See how this is working? And they'll also have the same color as the original object. Also, when I right click, I fire a special weapon. So by default, the special weapon fires out a bunch of bullets. And part of the bonus part of this assignment is actually going to be you creating your own really cool special weapon. And after the assignments are marked, on stream, I'm going to show off some of the really cool special weapons that people in the class created. Okay, so that's just a little demo of the assignment. Oh, also, bullets have a lifespan, and they also fade out with their lifespan. Similarly, these little enemies that get spawned after you kill something, they also have a lifespan, and they are going to fade out as their lifespan decreases. Once they fade out completely, they'll be destroyed. And I have a text file that I'll read that details the entire assignment. Let's just first look at kind of where we are in the course. So, assignment 1 is due tonight at 11:59 p.m. And at midnight, around midnight sometime, is when I'm going to release the zip file for assignment 2. And you'll have 14 days to complete assignment 2. It's more work than assignment 1 for sure, but as we'll see, it's not that much work. Once you start to get used to the ECS programming side of things, you'll really start to realize like how powerful it is and how creating these game mechanics and these game features are going to be really, really simple. So I do have a couple of PowerPoint slides. I think I'll go through these first, and then we'll read over the assignment description, and then we'll look at the skeleton code for the assignment. So let's look over the slides. So these are the slides for the assignment 2 game engine architecture. So here's the engine architecture progression so far in the course. Assignment 1 was just getting used to the C++ programming and the API for SFML. And so it was just a very basic program. Can you draw some shapes to the screen? And can you use SFML to draw those shapes? Maybe also like create a vector to store shapes in, just really getting used to C++ and the language itself. All of the functionality on the first assignment was inside the main.cpp file. So we only had one file in our assignment, and that was main.cpp. For assignment 2, here's what's going to happen. We're going to start separating our functionality of our game engine into different classes. We're going to write our own Vec2 class for 2D game math. We have the first appearance of ECS classes, so we're going to have entities and components in our game. We're going to have the entity manager, which handles all of the entity data for us. And we're going to have the ECS systems functionality in the game.h functions. Okay? So, here's what that's going to look like. We're going to have a bunch of different classes in a bunch of different files. Here, for example, we're going to have the game object. This is the main game engine object. The game object is going to store as class variables. It's going to have the window that we draw things to. It's going to contain the entity manager. It's going to contain a special pointer to the entity that is the player. We're going to have a boolean, which is whether or not the game is currently paused, and a bool whether or not the game is currently running. We're also going to have some systems inside the game function, inside the game class. These systems are going to be the movement system, the user input system, the rendering system, the enemy spawner system, and the collision system. We'll also have a function update, which is going to get called every frame, and an initialize function as well. Then we have the entity manager. I won't go over the entity manager because we did that in the last class, but the entity manager will have all that functionality that we talked about last time. Similarly, we're going to have the entity class, which we talked about last time, the Vec2 class that we talked about last time, and we're also going to have some some components that we'll be attaching to our entities. The entities for this assignment are going to have the following types of transforms. We're going to have the following types of components, excuse me. We're going to have the C transform component. The C transform component contains things like the velocity and the position of an entity. We're going to have a shape component. That's going to store the circle shape that we use to draw the entity with. We have the collision component. That's going to store the bounds of the collision so that we know when we collide with an enemy or when a bullet collides with an entity. We'll have an input component, so that'll hold whether or not certain buttons are being pressed in our game engine, and we can use that in our movement system to actually move. We'll have a score component, so when we kill enemies in the game, we actually get a certain amount of points, and so each enemy is going to have a score component, and when we kill an enemy, we're going to add the score component of that enemy to our own score. And we'll also have a lifespan component. So the lifespan component is going to be, it's going to give us a certain amount of frames, and after that number of frames has passed, then our entity we will destroy it. Someone said, looking at the C collision class, I assume we are treating the bounds of all shapes as circles. So how tough would it be to get pinpoint accuracy in terms of collision detection? Do games even normally do that? So yes, in assignment 2, all of our entities will have circular bounds. And as we go forward in the course, we'll be getting more complex bounds. Okay? So I won't go into the collision details because that's for another lecture. But yes, for the second assignment, we will only have the circular bounds. We're going to have the Vec2 class, which is going to have all different sorts of operators defined on it. And here, these are actually going to be floating point values, not double values. I don't know why I have this in the slide. So what will happen, and I'll show you this in the code, is that I'm going to give you the skeleton code for Vec2, and you're going to fill it out with the actual functionality. We're going to have several different components that I give you. These are going to be pure data. We're going to store shared pointers to these components within the entity class. And each component has its own class. And each component implements its own intuitive features on an entity. So for example, a score, a collision, etc. The entity class, again, entities are game objects. The entity is going to store pointers to our components, but we're going to be using shared pointers in this course. So over here, where you see C transform star, that's actually a shared pointer, but I didn't have enough space in the slide to include that. The tag is the type of enemy, or the type of entity, and that will be represented by a string up here. Active is whether or not this entity is actually alive or dead, so do we want to destroy it or keep using it? The ID is going to be an integer identifier that we construct each entity with. And the star here, just for example, for assignment 2, this is going to be a shared pointer. So wherever you see a pointer, star, that's a shared pointer. The entity manager class, this is our entity factory class, and it's got this delayed entity add functionality and delayed entity remove functionality that we talked about last time, which will help us get around iterator invalidation. It also has a secondary map from tags to entities, and I talked about that last time as well. And it's going to do all of our bookkeeping for us, like our memory management, etc. So the really new class that we're introducing here that we didn't have anything in any slide about so far is this game class. That's going to be the main class, and it's going to represent our game engine. Going forward, this game class is going to be expanded into multiple classes in the course, but for right now, we just have one game class. This is the top-level game object. It's going to hold all the game data. It's going to contain all the game system functions, and it's going to have all the gameplay code. So, what can this version of our game engine actually do? So it can create game objects as entity instances, it can add component data to entities, and it can implement the gameplay systems via the systems. And it can handle user input as well. You're going to be able to pause the gameplay and exit the game, and you're going to be able to initialize the game by loading a configuration from a file. So that's what we're going to be able to accomplish in this version of the game engine. What are the limitations of this game engine? So we can only display one game state or scene in this engine. We currently cannot load any textures or sound assets into the game. We'll be doing that in the next version of the engine. We cannot display any textured animations yet. That's in assignment 3. It doesn't have any menu or any sort of interface. It's just raw gameplay. So all of these things we will be adding in the next assignment. And just in case you don't know what a game state means, we covered this before, but a game can contain many different sorts of states that have very different logic or controls. So for example, in an RPG game, you might have the following different states, or scenes, as we're going to call them. I forgot to update this slide from last year. So we could have one scene, which is the menu or text or dialogue, for example, up here. We could have another scene, which represents the world map state. So here in Pokemon, you're walking around the world map. And we could have another scene, which represents the combat or the battle state, right? So we see this down here. And so how can our architecture allow for different game states? Well, going forward, we will show how that can be the case. So the game class in assignment 2. What is this? Did I put this in here? 1 second. Forget this slide. I think I included that in there by mistake. So what we're going to do now is we are going to look over the actual description of the assignment, and then we'll go through the code. So here is the assignment. And you'll be given this as well. And I'm just going to read through all of this to make sure I don't miss anything. Okie doke. So, for this assignment, for the submission of the assignment, for this assignment, you will zip and submit the entire SRC or source folder of the assignment. You are not allowed to add any files in additions to the ones that are already in the source folder from the assignment zip file. This means that you will not be submitting any changes you have made to the Visual Studio project if you used it for development. Now, you are not allowed to create new files, but you are allowed to create new functions within those files if you so need. So you must include the following info in a comment at the top of main.cpp when you submit. So all of the students' names in your group, whether it was solo or working with a partner, their CS usernames and their student numbers. And if you did not get a specific feature to work, please explain what you tried to do to get it to work, and partial marks might be given for effort. So for example, if you couldn't quite get a specific feature like bullets firing in the exact right direction to work, explain what you did and where you got tripped up, and we can give you partial marks for that. I'm a big fan of partial marks as long as you tell me what you tried. Okay, so here's the program specification. In this assignment, you will be writing the game that was presented in class. This game must have the following features, and I've broken down the features by entity type. So, the player. The player is represented by a shape which is defined in the config file, and I'll get into the config file in a little bit. The player must spawn in the center of the screen at the beginning of the game and after it dies, and it dies by colliding with an enemy entity. The player moves by a speed read from the configuration file in these directions. So the up is going to be the W key, left is the A key, down is the S key, and right is the D key. So pretty standard WASD controls. The player is confined to move only within the bounds of the window. So if you're moving left and you hit the left window, you have to confine the player there. The player will shoot a bullet toward the mouse pointer when the left mouse button is clicked. The speed, size, and lifespan of the bullets are read from the configuration file. And you are free to come up with your own special move, which is fired by the player when the right mouse button is clicked. This special move must consist of more than one bullet, which travels in an interesting way. The properties of the special move are not in the configuration file. So, what's the enemy functionality? So enemies will spawn in a random location on the screen every X milliseconds, where X is defined in the configuration file. Enemies must not overlap the sides of the screen at the time of spawn. So what that means is that when you create a random place for your enemy to spawn, it must be entirely within the bounds of the window. It can't be overlapping. Enemy shapes have a random number of vertices between a given minimum and maximum number, which is specified in the configuration file. Enemy shape radius will be specified in the configuration file. Enemies will be given a random color upon spawning. So what that means is that when you go to implement SF color RGB, you're generating a random value between 0 and 255 for each of R, G, and B. Excuse me. Enemies will be given a random speed upon spawning between a minimum and maximum value specified in the configuration file. And here is one of the most important parts. When large enemies, so these are the default spawn enemies, collide with a bullet or player, they are destroyed. And n small enemies spawn in its place, where n is the number of vertices of the original enemy. Each small enemy must have the same number of vertices and the same color of the original enemy. These small entities travel outwards at angles at a fixed interval equal to 360 degrees divided by the number of vertices. So for example, if the original enemy had 6 sides, then the 6 smaller enemies will travel outwards in intervals of 360 divided by 6, or 60 degrees. So yeah, that's pretty obvious, and let me show you that again. If I go over to the solution, if I destroy this enemy, which has like so many sides, then they will go out in a circle, but that many of them will go out. And here, for example, so 360 divided by 3 is 120. 360 divided by 5 is something. And so when enemies die, they spawn and they go out with equidistant interval angle from where the original enemy was. So that's what that means. Okay. Score. Each time an enemy spawns, it will be given a score component of n times 100, where n is the number of vertices that it has. Small enemies get double that value. If a player bullet kills an enemy, the game score is increased by the score component of the enemy that was killed. The score should be displayed with the font specified by the config file in the top left corner of the screen. drawing. In the render system, all entities should be given a slow rotation, which makes the game look a little bit nicer. Any special effects which do not alter gameplay can be added to the assignment for up to 5% bonus marks on the assignment. But note that assignments cannot go above 100% total marks. So the 5% can overwrite any marks lost in other areas of the assignment, but you can't get like 105 on the assignment. So for example, if there was some other functionality that you didn't get to work, but you had some cool bonus marks, you could get up to 100% using that. An entity with a lifespan is currently alive. Oh, sorry. I think I phrased this weirdly. Any entity with a lifespan is currently alive. It should have its color alpha channel set to the ratio depending on how long it has left to live. For example, if an entity has a 100 millisecond lifespan and it has been alive for 500 milliseconds, its alpha channel should be set to 0.5 times 255. This ratio should go from 255 when it's first spawned to 0 on the last frame that it's alive. And actually, since I wrote this config file, I missed this. We have changed lifespan from a number of milliseconds to a number of game frames. So for example, here I'm going to say 100 frame lifespan, and if it has been alive for 50 frames. Okay. So I've changed that, and so I want to change it in the assignment description as well. Here's some miscellaneous things. When I press the P key, I should pause the game, and I press the escape key, it should close the game. So I want to show off the pausing functionality. So I can shoot some bullets here and hit the pause key, and when the game is paused, all the updating of all the entities... Oh, I'm getting the bots today. Look at this. Ban. Okay. When I pause, everything in the game stops moving, and I can no longer click, but things keep rotating and they keep animating. So that's what you have to implement in your assignment. And then you can unpause as well, etc. The configuration file. So the configuration file will have one line each specifying the window size, font format, player, bullet specification, and enemy specifications. And so this is very similar to the first assignment, so you're already pretty comfortable with this. Here is an example of the config file that I give you. So up here, we have a window. The window is going to have a specific format. The player has a specific format. The font has a specific format, etc. Okay, so here's the format of that. Window, WHFLFS. This line declares that the SFML window must be constructed with width W and height H, each of which will be integers. FL is the frame limit that the window should be set to, so if that's 60, that means it's 60 frames a second. And FS will be an integer which specifies whether to display the application in full screen mode or not. So you have to go to Google and say, hey Google, how do I put SFML into full screen mode? And that turns out to just be a little flag that you pass into the constructor. So here, for example, this line says window 1920 by 1080. That means that the window is going to have 1920 pixels width by 1080 pixels height. It's going to have a frame limit of 60, so that means it will run at a maximum of 60 frames per second. And this is 0, meaning that it will not run in full screen mode, so it will run in windowed mode. Okay, so now we'll move on to the font. Font is the exact same as assignment 1. So font is FSRGB, where F is the string, which is the font file, S is the size, so the character size, and RGB is the font color. So you've already done that for assignment 1. The player specification is a little bit verbose, but we have a number of variables for the player specification. So the first one is SR, that's shape radius. And that's going to be an integer, and that defines the shape radius of the player. And I'll show an example of that in a second. CR is the next variable, and this is going to be the collision radius. So actually, let me bring up I'm going to bring up the Blackboard again. I closed my Blackboard by accident. Okay, so we're going to have the player object. Oops, let's try white. I think white is a little easier to see. So we're going to have the player object, and this radius right here, this is going to be SR, or shape radius. This is the drawn radius of the player on the screen. So there's also a CR, and that CR could be the same as SR, or it could be different. So for example, let's say our CR is like this. So then this would be our CR. CR. So CR determines the collision radius. So if we have an enemy over here, and if the enemy looks like this, okay, and it has a collision and shape radius of this, even though it might be overlapping with the shape radius of our entity, it does not collide with the entity unless it actually overlaps with the collision radius of our entity. And this is an important distinction, that collisions are not directly tied to the animation that we're playing, okay? So whatever shape we're drawing, that shape radius is not necessarily the actual collision radius. Now, in most cases, when you're creating a game, you would want to have the shape radius be the same as the collision radius in order for your player not to get really frustrated. But maybe you do want to be a little bit lenient so that if the enemy slightly clips over your player, that is not a collision. And so that's why there's a difference between the shape radius and the collision radius. And someone in the chat said, bullet hell players are thankful for this. Yes, so there are some games where like there's lots of bullets on the screen, and for example, you might have a spaceship as your entity, like this in some games. This might be like how your entity is actually drawn, but the collision, like what actually collides with a bullet, might only be this big. And so it helps the player by making it a little easier for them. All right, let's go back to the configuration file. Next, we have a speed. And so this is S, this is a floating point number. And remember, the speed is, okay, I'm going to bring back the blackboard. So let's undo all this. So the speed is given as a scalar value. Oh, that is the worst for colorblind people. Oh my. Okay. So speed is going to be given as S, okay? So if an enemy has a speed of S, it does not mean that every frame they move S units in the X direction and S units in the Y direction. No, no, no. That is not correct, okay? That is not correct. It means that whatever path they're traveling on, they have a total distance traveled of S. And so you're going to have to go back to the notes and refer to, okay, well, if I have a given speed and a given direction, how do I get the actual update vector to move that enemy within the screen? And this is actually the player, so this means the player's speed. We have a fill color. So the player now is defined by two colors. So the fill color, FR, FG, and FB. So for example, if I have this here, and I have a color, and let's say I have a different fill color. So for this shape here, the fill color is light blue, and the outline color is yellow. Okay, so that's the difference here. We have both a fill color and an outline color for our shape. Also, we have an outline thickness. And our outline thickness, outline color, and fill color, these are all properties that we can set on the shape of an SFML object. So this will be really easy to implement. And also we have V, which is the shape vertices. Okay. So I just had a question in the chat. Oops. How is the one-dimensional floating point scalar S different from the vector, right? So our shape or our player is going to be moving in a specific direction. And so if we hold up, so if all we're doing is holding up on the player, right? Then if we're holding W, we're moving up. And so our total speed should be S, right? And if we're just holding up, then that's a very easy calculation. Our Y component of our movement vector has a value of S, and the X component of our movement vector is going to have a value of 0. But if we're holding both W and A, we can actually move diagonally. So in that case, if we're moving diagonally, for example right here, and our speed is S, then the magnitude of this vector is S. But in actual fact, in order to move the entity, we need to know the X component and the Y component that we have to update it. So the speed of the entity is S, but the velocity of the entity is here with an X and a Y component. And so what we do is we take S and we break it down into its X and Y components, and then we have to add the velocity to the position. So that's the difference between a speed and a velocity. Okay, let's go back to the configuration file. Next, we have the enemy specification. And the enemy specification is identical to the player specification up until about this point. Okay, so I'm not going to repeat all of those. Next, the things that are different is we're going to have Vmin and Vmax. So Vmin and Vmax are the minimum and maximum number of vertices that an enemy can be randomly spawned with. So whenever you spawn an enemy, you're going to give it a random number of vertices in its shape between Vmin and Vmax inclusive. Next is L. This is the lifespan in game frames of the small enemies. So if we look at, where am I here? 4300. I gotta go back. Assignments, A2, bin, solution. Okay. If I shoot an enemy, you can notice that the smaller enemies, oh my god, I can't even shoot it. The smaller enemies disappear after a while, okay? That's their lifespan. And so after that L value is the value of the lifespan of the small enemies. Okay. Also, we have a spawn interval, SP, and that'll be given as an integer. And so the spawn interval is going to be a number of milliseconds. So for example, if this is set to 1000, then every second we are spawning one enemy in the game. If it's set to 500, we're going to be spawning 2 enemies every second. And you can go to the SFML documentation, and if you want to be able to time things down to the millisecond in our programs, you can actually use the SFML SF clock object. Oh, I'm sorry. This is the problem with live lectures. I haven't changed this yet, but this is actually going to be given in game frames as well. So last year, we ran into an issue when we were spawning things using an actual clock timer. And so the spawn interval is going to be given in game frames as well. So all of our timing is going to be done with in-game frames and not with wall timers, okay? So not with an actual clock on the wall. So the spawn interval, if this is set to 60, then what we're going to be doing is spawning, if this is set to 60 and the game frame limit is set to 60, then we are going to be spawning one thing every second, effectively. Similarly, if our frame limit is set to 60 and this is set to 120, then we will be spawning one enemy every 2 seconds. Now, lastly, we have the bullet specification. And again, the bullet specification has approximately the same thing as the player, except it has a lifespan. So the bullet specification is almost identical to the other things. So you can just read through here and read those values in. Okay. So I'm going to go over to the assignment code now and step through just a little bit of the game code. So you can see over here on the left, and I know this font is a little bit small, so I apologize for that, that we now have multiple files in our project. And all of these files are in the source directory of our project or our assignment zip file. So the Visual Studio project is going to load all of these files up for you. And if you run the default program that I give you, what you'll get is the following. So I have spawned the player object, but it can't move, it can't do anything, and it's just slowly rotating down into the corner. And that's all that happens. So that's what happens by default. So what do we have to do in our assignment? The first thing we have to do is implement the vec2 class. So down here on the bottom, this last class is vec2. I have given you the header file for the vec2 class. So remember before I was saying that we're going to, in C++, we often separate the functionality of classes into a header file, which is the class and function declarations, and a CPP or implementation file where the function definitions are. And so this is going to be a little bit new to some of you, but this is the vec2.h, this is the header file. So we can see in the header file for the vec2 class here, all we've done are the declarations. And so the declarations, meaning that we've said which functions exist for the class, but we haven't actually shown the code for that class. And then the way we split this into a header file and a CPP file is that in our CPP file, we include the header file, which has all of our declarations, and then we include any other things which we might need to do this. And then we specify all of the definitions of those functions. So here, for example, I'm going to say, I have to declare this, well, it looks like before we saw this as a namespace, but in order to define the functionality of the vec2 class constructor, this is the default constructor, we say vec2 : vec2. Now, let me go down to here to explain this because it'll be a little more obvious. So here's how we would define, say, if we look at our header file, we have a function which returns a float, it's called dist, and it's going to take in another vec2 as the argument, okay? And what this will do is it will take in another vec2 and compute the distance from this vec2 to that vec2. And so the way we specify the functionality of that function in the CPP file is by saying float, and then right before the function name, we say the class name, which is vec2 : So if you're coming from Java, yes, this seems a little bit verbose. You would just put this all in the Java file, but this is the syntax in C++. Outside of the header file, we have to declare exactly which function this is, and this is the dist function of the vec2 class. Okay, so that being said, this is where you have to do the implementation of each of those functions. Now, this is really, really simple, okay? I've already done the constructors for you. Let's just do the plus operator as an example, and we actually did that last time. So the plus operator, you can do that super, super easily, where you just say, I'm going to return a new vec2, and that's going to be my x value plus rhs.x, and the second component is going to be my y value plus rhs.y. And that's it. That's the implementation of this function. It's really easy, okay? Here we have other things like multiplying by a scalar, dividing by a scalar. This is bad. I said not to do this. You guys should be calling me out on that. So primitive types should not be passed by a reference. They should be passed by value. Okay, so you have to implement all these functions for which I've given you the skeleton code. Okay, so I'm going to put back these comments. And this is the thing that you have to do first, because if you don't, then all of your vec2s will just be equal to 0, 0, and that's no good. All right, so then once you have the vec2 class done, what you're going to want to do is come over. Some people are asking questions about the syntax of C++. Please go back and watch the lectures on C++ where I explained all of that. I can't keep going backwards in the lectures. Next we have the entity class. So as you can see, the entity class has the exact functionality that we said in the slides. So it's going to contain a shared pointer to all of our different component types, and I'll go over the components in a second. It's also going to have the active Boolean it's going to have the integer ID, and it's going to have the string, which is the tag. Down here, it's going to have, since these values up here are private, we have to have some functions to get access to those. So we'll have functions such as isActive. We'll be able to get the string as a const reference. This should just be size t. And then we're also going to have a function destroy, which means that we will be setting the active part of this to false. And we talked about that last time as well. Then I've implemented all of the functionality of the entity class for you, okay? So the entity class's functionality is done. You do not have to touch the entity class. That's really good. And let's have a look at the components now. So the components each have their own class. So you can see here is the transform component. So the transform component of each entity is going to store 3 things for this assignment. As we go on, they're going to get more complex though. So the first thing is the position, and this is stored as a vec2. So we're going to have a vec2 position, and this is the position of the entity. Similarly, we're going to have a velocity, and this is essentially the speed in the x and the y direction that we should update, or the magnitude of the velocity in the x and the y direction that we should update the position by every single frame. Then we're going to have the angle, and the angle is going to be what we use to rotate the entities on the screen. Now, I've done the constructors for you, so you don't need to worry about that. But a C transform takes in a vec2 position, a vec2 velocity, and a float angle. The shape component, or the C shape, has only one member variable, and that is an SF circle shape. So remember when I talked about how we can represent all regular polygons by a circle shape? That's what we're doing here. So if we attach a shape to something, then it will be drawn with this shape. So the shape component is going to take in its constructor a number of arguments. And these arguments are the radius of the shape, the number of points, the fill color, the outline color, and the thickness. And in here, in the constructor, what I do is I construct the circle with the radius and the points, and then I set all of these values for you. And so the shape component, all the components are already done for you. Next, we have the collision component. And the collision component, again, just stores the radius. So importantly, remember this, the shape component is what is drawn, but the collision component is what you actually use to do the physics. Next, we have the score component, and we just store an integer score in here. Then we have a lifespan component. Now, a lifespan, if you think about it, is going to have 2 different components, or 2 different variables. The first variable is the lifespan of the enemy. So for example, if we're running our game at 60 frames per second, and we want our entity to live for 1 second, then we would set our lifespan equal to 60. So I guess there's 2 ways that you could do this. In one way, you could decrease that lifespan by 1 every frame. And you know what? Let's just do that. So, editing the assignment live. Why not? Okay, so here's how we're going to do the lifespan component in this assignment. When we construct a lifespan component, we're going to give it a value, right? So for example, if we want the enemy to live for, or the entity to live for 60 frames, we set this value equal to 60. And then what we do in our lifespan system, every entity that has a lifespan component, what we're going to do is we're going to decrease the remaining lifespan by 1. No, I can't do that. All right, I got to go back to what I was doing. Apologies, I can't edit this out of the video, but I knew there was a reason that I did it this way. And here's why. Okay. Lifespan has to have 2 variables, and I apologize again for trying to edit this live and messing it up. It has to have 2 variables because of the way we're doing something later. So, the 2 variables are the total duration of the lifespan. So for example, again, if we wanted this to live for 60 frames, we would pass 60 into here. Secondly, we are going to record when the entity was created initially. Okay? So, what we're going to do for this is we're going to pass in the current frame of the game into the lifespan component. So the lifespan component keeps track of two things. It keeps track of the total lifespan, and it keeps track of what frame of the game this thing was created on. So now all we have to do in order to tell whether or not we should actually kill a component whose lifespan duration has expired is just by saying, take the current frame of the game, subtract from that the frame that we created, this entity with a lifespan. And if that difference is bigger than the lifespan of the entity, then we kill it, right? So for example, if our lifespan was 60, and we created so let's just put these values here. If we had a lifespan of 60, and we created the entity on frame 100, then what would happen is on frame 161, for example, we would say, okay, 161 minus 100 equals 61, which is greater than 60, and therefore this thing has to be destroyed. And I'll show you the place in the code that you have to do that. And lastly, we have the input component. The input component contains a bunch of booleans representing whether or not the button has been pushed in the input. So for example, here, in our input handler, our SFML input handler, if we detect that we push the up button, then we're going to set the up variable of the player's input component equal to true. Similarly, if the A key is held, we're going to set left to true, and when the A key is released, we're going to set left to false. And so these are the controls that we're going to use in our game. Okay, so those are the components, and again, I sincerely apologize about messing up the definition of that lifespan for you. Okie dokie. Now we will go to the game class. So in the game class, wherever you have to add code, I have put in a to-do, all right? So people who thought the course was moving slowly, here's where it starts to pick up. There's a lot of programming in this assignment. In the init function of the game class, this is where you have to read in the config file. And what I've done for you is so that, remember in the first assignment, when you had to, in the first assignment, you had to read in a bunch of different properties of the shapes. And some of you created your own classes, some of you did different things. But here what I've done for you is I've already created these pre-made structs. And these pre-made structs have instances within the game object. So what you can do down here, for example, if you have your standard IF stream, so this is your file in, this is your config file input, or your input stream, and you construct this based on your path, right? This is the syntax that we looked at for file reading. And for example, if you're on the current line for reading in, for example, the player configs SR, CR, FR, then what you can do is you can say fin, and I've created these variables for you. So the player config, so m player config dot sr, m player config dot cr, etc., etc., etc. Okay, so you have your loop here. It says like if it's the player part of the config file. So if this says player, then I'll start reading in these things. Right, and so that's similar to assignment 1, but here you can just create them right here. Now, once you've read those in and later you go to create a player object or you go to create an enemy object or a bullet object, you can read the variables from these class variables that I've already defined for you. So that's just to eliminate some of the confusion. Here I have these things and all the variables are already there created for you. Okay. Next we have the run function. So the way where we just had a main loop last time, remember in our last assignment we just had a main loop? now we have some different functionality. So now, instead of just saying, okay, run forever, and if I exit the system by pressing the X button, I just quit the program, now we have something just a little bit different. Inside the game class, I have a Boolean called running. And what happens is, inside this run function, I'm going to loop while this running variable is equal to true. So let me see how this is called. Out in my main function, so now this is the entire main function. It's really, really easy to use. All you have to do to run the game is create a game object, give it a variable, so here I've just called it G, and into the constructor we pass the config file. And then all you have to do is say game.run, and our whole game runs for us. So this run function inside the game class has the while loop that was the main loop of assignment 1, but it's a little bit more complicated. So what happens now is that the main while loop of the game's run function calls all of the different systems in order. So what it's going to do is first update the entity manager, and we'll get to the entity manager in a couple of minutes. It will then call the enemy spawner system, then the player movement system, then the collision system, then the user input system, and then finally it will render the frame. And then once all that is done, the game's current frame gets incremented, okay? So that's what this is. Now, you have to add the pause functionality in there. So some of the systems should function while paused. Some of the systems shouldn't. So I've already given you a Boolean here, which is whether or not the game is paused. And so what you can do is in the input handling, which I'll show in a little bit, is you can toggle that on or off whenever the P key is pressed. And so what you want to do is you can say, for example, if not am paused, well, what do you want to do if the game is not paused? Maybe you want to call some of these functions, maybe you want to call other functions, I don't know. So certain functions should be called when the game is paused and certain functions shouldn't, and that's the Boolean variable that you're going to read in order to implement that. Down here, we have the set paused function, and I just have a Boolean paused, which is, you just set the paused function in here. Next, I have the spawn player function. Let me go out here for a second just to show you the functions that we have on the game class. So we have one function for each of the systems, and we also have a few helper functions. So rather than trying to write all the code to spawn the player or an enemy or a bullet inside a big while loop, we're going to have functions that take care of this for us. Those functions are as follows. So we're going to have a function to spawn the player, and when that's called, the player is going to be spawned in the middle of the game map. We're also going to have a function which spawns enemies. We're going to have a function which spawns small enemies, and that function is actually going to take in the pointer to the entity that was killed in order to spawn this enemy. We're going to have a function which takes in, a function called spawn bullet, and this takes in two parameters as well. The first one is going to be the entity that did the shooting, so that's going to be the player in this case, and the second parameter is going to be the mouse position that we clicked inside the window that we want the bullet to travel toward. The last function is the spawn special weapon function, and we want that special weapon to be spawned at the position of the entity that shot it. So normally that will be the player. So those are all the functions, and now I'll go over those. So the spawn player function, if you remember, when I launched the game, something happens here, right? So what happens? Well, the player was spawned here with a given color and a given outline color with a thickness, and it was also given a velocity. So let's just look at how I did that. So you're going to get really, really familiar with this, and this is the main way of how you spawn entities in an ECS system. And I got to take a drink. All this talking today, oh my God. How's my voice? Does it sound broken? I feel broken. Someone said I sound like a person that I've never heard of. Sounds just fine. Okay, good. So, to do, finish adding all properties of the player with the correct value from the config file. So this is just an example that I've put here for you in order for something to appear on the screen. But this is not the full file. So just like I showed before in our examples, we create every entity by calling entitymanager.addEntity with a tag. This returns a standard shared pointer entity, so we just use auto to save typing. So what auto does here in C++ is I could have initialized this by doing this, but C++ knows that this function returns only one type. So if I say auto, that's essentially just typing in standard shared pointer entity for us. So if we look back here, the entity manager inside our game object is this m_entities variable. So we say, hey, entity manager, add us an entity with the tag of player, and then give us back a reference to that. Perfect. Now what we want to do is we want to give it a transform so that it spawns at position 200, 200 from the top left with a speed of 1, 1, so it will move 1 pixel in the X and 1 pixel in the Y every frame. So this is supposed to be velocity. And it's going to have an initial angle of 0. So the syntax for that is we say, hey, entity, you have a transform shared pointer. I'm going to overwrite it because initially it's just null. So I'm going to say that the transform, and now I'm going to say standard make shared C transform because that's the preferred way of constructing a shared pointer to a C transform. And the arguments here are the arguments of the constructor of the C transform. So if you ever forget what they are, go back over to the components.h, and you can see that the C transform takes in 3 variables. First is the position, then it's the velocity, and then it's the angle. So if I go back over here to the game, I can see that I'm passing in 200, 200 as the initial position, a vec2 of the velocity, which is 1 and 1 in each of the x and the y, and a 0, 0 for the initial angle. So if I click run, then my entity will be spawning at approximately 200, 200 from the top left, and it will be moving 1 pixel per frame downwards and to the left, to the right. Now, it's not good enough just to give it a transform because we actually want to be able to draw it, right? Something has to be there. And in this assignment, we are drawing a shape component. So now we have to overwrite the entity's shape component as well. So we're going to add a shape component, and into that shape component, we pass the parameters of the shape component. So if we go back to component.h, and we go down to shape, here's the order in which those parameters are. It's the radius, the number of points, the fill color, the outline color, and the thickness. So for example, if I go over here, let me just play with some of these. If I pass in, instead of 32, I pass in 64, then the shape that gets drawn is going to be way bigger, right? You can see that. Similarly, if I had passed in 2, 2 as my velocity, then my shape will be moving much faster. Oops, I hit compile before it saved. So now it's moving twice as fast, right? So you can start to see the power of ECS already. If I want to change the color of the fill color, maybe to a green, then I just pass 255 in here. Okay, so now it will be filled green. If I want to change the outline color to, say, blue, then I will set the red component to 0 and the outline color to 255. And now it'll have a blue outline. So let me just undo that because it looks a little nasty. Okay. Similarly, I could make it super thick by changing the thickness to 8, right? And now I have a super thick player. Make all the jokes you want. All right. So, for example now, one of the things you are going to have to do in order to get your assignment to work is add an input component to your player. So let's go add an input component to the player. The way you would do that is entity C input, which is the input component, equals standard make shared C input, and then the parameters to C input. Now, I forget what they are, so let's go to components. We go down to C input, and oh look, there are no components, there are no parameters to the C input. It will just start up everything as false. So this is something that you have to do in the assignment in order to use your input components. Now, I said that the entity manager stores all of the components with no exceptions, okay? The only thing that we're going to use as an exception in this course is that we're going to store inside the game engine just one little tiny shared pointer to the player object. So this player object still lives inside the entity manager and is still managed by the entity manager, but we just have an extra pointer to it called mPlayer. And the reason for that is because we're going to have to refer to the player so much, and we don't want to have to be iterating through all the entities to find the player every single time. And so what we do is we make sure that we set this internal variable to the entity that we just set up inside the spawn player function. Okay, so that's the spawn player. It is incomplete. You have to finish this function in order to get this to work properly. Maybe I'll just leave this here for you so that we can use inputs. Because last year there were a number of people who tried to do this and they got null pointer exceptions because they forgot to put this in. So maybe I'll just leave that there. Now, I have put in hard-coded values for all of these. But what you actually have to do, this parameter here, for example, this is the player's shape radius. So what you have to do is after you've read that in, you have to read in the player config and pass in the shape radius of the player, okay? And similarly, for all the different values here, you have to add those in as well. Okay. Now, there's the spawn enemy functionality. This was incomplete. Must be spawned completely within the bounds of the window. So what does this mean? So based on the README file, you read through the README file and you say, okay, well, in order to spawn an enemy, what's my enemy going to have? Well, it's going to have a transform component. It's going to have a shape component, right? Because I want to draw the transform. It has to have a position and a speed. It's going to have a shape component because it wants to be drawn to the screen. It's going to have a collision component because we want it to collide with the player and bullets. Let's see what else an enemy might have. What do we have here? Oh, it has a score component. So we're going to have to add a score component here. And the score component, remember, it gets initialized with the number of sides of the enemy, etc. Now, when we are creating enemies, we have to give it a random position within the bounds of the window. So for example, to get our window, like our window's leftmost value is always 0. So window left equal 0. Window right equals mwindow.getSize.height. Remember, so we used that from last time as well. So this window object, this is how we can get the bounds of the window. Now, what happens here is that we want to spawn the enemy within the bounds of the window. So what we actually need to do is move this left over by a little bit. And let me just show you what I mean here. Let's go to the blackboard. So we have our window like this. It has this is going to be 0. It has a width. It has a height, right? So this is going to be height, this is going to be width, this is going to be 0, this is going to be 0. And we actually also have a shape that we're going to be drawing for our enemies. And so if this is the radius of our enemy, then we have to add that to all the bounds of our windows when we generate the random position of an enemy so that we don't spawn it partially off the screen. So when we actually spawn one of our enemies in the game, they have to be between these new bounds. Okay, so you add the shape radius to 0 to get the left, you add the shape radius to the top, or to 0 to get the top, you subtract it from the width to get the right, and you subtract it from the height to get the bottom. Okay, so that's where you spawn your enemies. All right. What else is in the components that we might need? Well, it looks like that's it. That's how you set it up. Now, what you're going to have to do here is you're going to have to say like float or position x equals random number between calculated bounds, right? And then position y equals random number between calculated bounds. And then your vec2, which is initial position, is going to have the values of x and y. And then when you go to create the C transform of your enemy, it's going to be spawned there for you. Okay, so I'll leave the rest to you. And the important thing again is that you have read some of these values in from the configuration file. And so if you go to the game, you see that we have an enemy config. An enemy config has all of these values. So one of the other values that you want to do is spawn the enemy with a random number of vertices between vmin and vmax. And so you use the code that I gave you in the slides for generating random numbers in C++ between a minimum value and a maximum value. And what you have to do there is you have to read m_enemy_config.vmin and m_enemy_config.vmax and spawn random number in this range, and then that gets passed into the circle shapes component. All right. So I had a question in the chat. Can we create helper functions like vec2 random enemy position? Yes, you could if you want to. So like I said before, if you want to alleviate some of the burden of code from this function, you could create a function which is random enemy position that returns you a vec2, which is the initial random enemy position. Okay, so that's the spawn enemy function. Now, when an enemy collides with something, you have to spawn a small enemy. And you're doing that inside this function. So again, you would say auto entity equals m entities dot add entity, and you might say small enemy, for example, right? So that's how you get an enemy from the entity manager. And then again, you would add a shape component, you would add a collision component, you would add all this kind of stuff. I had a question in the chat. Can we implement smarter spawning, like not letting it spawn near the player? So extra functionality like that you can implement. Just please document it at the top of the main.cpp file so we know what you did. Okay. Now, something very special has to be done within the spawn small enemies. And let's go back and look at what that is. And if you remember, the small enemy that gets spawned when an enemy dies has the same color as the parent enemy. And it also, we have to spawn as many of them as there are vertices in the original object. Okay, so that's what we have to do. So that's why we have to pass in the entity that was sort of the parent entity or the larger entity into here. Because when we create the smaller enemy, we have to read the values of the original enemy. So we have to set each small enemy to the same color as the original. we have to spawn a number of small enemies equal to the vertices of the original enemy. So what we're going to do inside the small enemy spawn function is actually going to be a loop, which is like for int I equals 0, I is less than e, so e is the entity. This is going to be the C shape component, and then the C shape component has the circle variable, and in here we're going to have, I think the function is get point count, I++. So this is how you would read the variables that we need to read from the original entity, okay? So we loop through until we get to this point count, and we're going to say in here, this is my small entity that we've added, and we set the parameters of the small entity. The other thing that you have to do here is you have to say the angle that you initially spawn at. So here we're spawning, let's say we're spawning 6 enemies. So for example, say the entity E had 6 points. So we are going to spawn 6 small enemies. So now you have to have something like float angle equals 360.0 divided by 6, or divided by this amount, right? So this is the angle at which you have to spawn each small enemy. So let's go back to the blackboard because I want to show how this is done. All right, so let's say we had an enemy which had 6 sides, like this, okay? So this was our original enemy. What's going to happen when we spawn our small enemies, when this one dies, is that they're going to spawn at the center position of the original entity, and they are all going to go outwards in the direction. So it doesn't matter what the original angle is. So for example, you could use 0 degrees as the original angle, and then you're going to spawn these at, so our theta is going to be equal to 360 divided by V, and V here is going to be 6, which is equal to 60 degrees. So we're going to say this is 60 degrees, this is 60 degrees, this is 60 degrees, this is 60, and this is 60. And so the small enemies are going to have a speed that's given in the configuration file by the original enemy speed, okay? And they're going to be flying out at a certain angle. Now, in the slides, I specifically gave you a slide that given a speed s and an angle theta, how do we determine the vec2 that's going to be its velocity? And so you'll use that to do this, okay? Oh, my throat. All right. And one other thing that's going to happen is, and I'll show that when I get to it. So that's how you spawn the small enemies. And that's probably going to be the most tricky part, right? Save that maybe till the end. We're also going to have a spawn bullet function. And so the initial position of the bullet has to be spawned at the initial position of the entity that spawned it. Also, we're going to have a target position, and that target position is going to be defined by the location of the mouse when we click. We're also going to have the spawn special weapon function, and this is where you implement your own special weapon. So again, spawn bullet, we have auto bullet equals entities dot add entity, and we would say, hey, this is a bullet. Right? Pretty easy. And then we would add all its components and do the specific logic. And the logic here would be the setting of the velocity and the initial position of the bullet, and its bounding box and its shape, etc. And we have bulletconfig.sr.cr.r.g.b, all that kind of stuff that we are using to spawn that. Okay, now we get to our first real system. And so the systems are where we do all of our logic. And now the reason I'm going a bit over time with this lecture, and it's because subsequent assignments will have very, very similar systems to this. So I'm going to explain them all here, and that's how you're going to know going forward it's going to be very similar. So the movement system, all of these systems are called in order once per frame. So for example, if we want our entities to move, then we have to somehow add its position. Sorry, we have to add its speed or velocity to its position. So here what I've done for you in order to make the default player actually work is I've implemented a very, very basic just add the x component of the velocity to the x component of the player. Now you may ask yourself, why didn't I do this? Why didn't I just add the vec2 velocity to the vec2 position? Because I have the vec2, I can add those together, right? Well, I can't because I didn't put in the functionality yet that you have to put in. So that's why I didn't do it that way. And down here, you can see that if I comment these lines out, so I'm no longer actually adding the velocity to the speed, then my player won't actually move anywhere in my function, or in my game, sorry. So I'll bring that back out. Now, the second system is the lifespan system. So in here, you have to loop through every entity. And you have to say, for example, if it has a lifespan component, do something based on that lifespan component. So the logic here is if it has a lifespan component and it is alive, we have to scale its alpha channel properly so that it fades out linearly with the remaining lifespan. And if it has a lifespan and its time is up, then destroy the entity. So here's one way that we could do something like that. So we can say for auto E, which is entity, in M entity manager, or entities, dot get entities. So this is how we can loop over all of our entities, okay? And no, we don't want a reference here because we actually want to copy the shared pointer to be correct. So we say for auto E in entities.get entities, and this will give us all of our entities. Now, if I ever want to see whether or not an entity has a component, well, if it doesn't have the component, then its shared pointer is going to be null, and null will evaluate to false, so I can say this. If E dot, or sorry, E is a pointer, so if E arrow lifespan. And what this will do is it will evaluate the shared pointer, and the evaluation will return the pointer, and if it's null, then it will be nothing. So if it doesn't have a lifespan, then this will be false. Okay? So I could say if the entity has a lifespan, then I want to do something. And in here, I can say, okay, what is the lifespan remaining? So I'll just do that calculation for you here, and then I'll stop. So I can say int remaining equals, and now in order to get the lifespan component, I just go E, see lifespan, and this has two variables. It has the lifespan and it has the frame created, right? So the frame created is what I'm interested in. So if I subtract the game's current frame from the frame that I created the lifespan component, then I get how long the entity has been alive. But what I actually want is how much time remaining in the lifespan of the entity. So in order to get that, I have to take this and subtract it from the actual lifespan duration of the entity. So this will give me how many frames remaining the entity has to actually live. So now I could say, for example, if remaining is less than or equal to 0, then I want E destroy. Right? So I want to destroy the entity that way. Otherwise, if it's not, then what I want to do is get the ratio of the total lifespan of the entity to the amount of time I have remaining, and then multiply by that 255, and then scale the alpha channel of the actual entity itself. But I don't want to do the assignment for you, and that part's a little bit tricky and a little bit fun, so I'll let you do that. Now, here we implement all the proper collisions between the entities. Be sure to use the collision radius and not the shape radius. And in here, there are two things that we want to do. The first is check collisions between player and entities. Okay, so we do something like this. For auto E in mEntities.getEntities, and here, this will be enemy, right? Auto E in entities.getEnemies. So that will return the vector of all the enemies rather than the vector of all the entities, including, say, the player and the bullets. We can say if collision between E and player, spawn player, and destroy enemy. We may have to do the same thing for the small enemy. Right? Okay. Now, we also have to check collisions between enemies and bullets, but there may be more than one bullet on the screen. So in order to check for bullet collisions, we could do the following. For auto B in mEntities.getEntities bullet, right? This gives us the vector of all the bullets. And then I can say for auto E in enemies, right? So you can see now how this entity manager, this is really good. So if there's a collision between E and B, then we want to kill both B and E, right? And not only that, but when the enemy is destroyed, here is where we're going to detect the points component of the enemy and add it to our current score. And inside here, I have an integer score, and that's what you'll implement. That's what you'll increment. So class time is already up, but I'm going to keep going because I've been going into more detail than I usually do. Like last year, I just kind of gave them this and told them to go nuts with it. In the enemy spawner, what you have to do is you have to, I'm going to delete this, and you're going to, this is the code which implements the enemy spawning. And we're going to be using frames, okay? So I'm going to before I release the assignment, I will code this up with how you're supposed to do it. But essentially, what you're doing is you're counting the amount of frames since the last time you spawned an enemy, and then you spawn another enemy and reset the counter, okay? That one, and inside enemy spawner is where you call the spawn enemy function. So essentially, if enemy spawn timer elapsed, spawn enemy. That's what this function is. Okay. Now, right here, what I have done in the render function, I have only done the code which draws the player. So here I have hard-coded the drawing of the player entity, and I've also done things where like I give the entity a little bit of an angle, and then I rotate the player entity. And by setting the angle and setting the rotation equal to that angle, then what I get when I run the program is this tiny rotation of the player. So essentially what you have to do in this function is you have to change that. So instead of just drawing the player, you say for auto E in mEntities.getEntities, if it has a transform and if it has a shape, I have to do that. So essentially what you do is you take this, you copy and paste it in here, and you change this to E, okay? With maybe one or two other little changes. But you go from rendering the player to rendering all the entities. And the last thing is the handling of the input. Okay. Well, the last thing for the game class. We still haven't talked about the entity manager. Whew, lots of talking. And again, I know the explanation of this assignment is like pretty deep, but once you're used to this architecture, this is the same architecture we're going to be using going through the whole course. So in the next assignment, I won't need to explain anywhere near as much of this because you'll already know all of this. So here's how the window events are going to work. It says to do, handle user input here. Note that you should only be setting the player's input component variables here. You should not implement the player's movement logic here. The movement system will read the variables you set in this function, and I'll explain what that means. So just like before, we had some events that we were detecting. So for example, if the event type is window closed, then instead of exiting the program, what we do is we just set, hey, mRunning equals false. And when we set mRunning equals false, the run function will terminate, and then the program will stop running. Now, here we have the key event handler example that I've given you. So here we say if the event type is a key pressed event type, then I can use a switch statement on the event.key.code, and if that variable event.key.code is equal to SF keyboard W, which is the integer code corresponding to the W key, then I'm going to standard C out W key was pressed. So if I go back and run the program and I press W, over here I see W key pressed and I also see W key released. So what you have to do here is set the player's input component up to true because W is the up key. Similarly, I have to detect the event when the key is released as well. And when the W key is released, I want to set the player's input component to false. Now, you also have to do this. You have to do this for the W key, the A key, the SD key, and the D key. And so you have to duplicate all that code. You can just copy and paste the case, but remember the break part of this. You have to have the break part of that and look up the syntax for C++ switch statements. It'll help you out. The second type of input event is a mouse button pressed. So when the mouse button is pressed, you want to spawn the bullet, which is going to head towards the mouse position that you pressed. So here you detect the event when the left mouse button was pressed. And right now, what I've done is just included some sample code for you, which prints out to the console, left mouse button was clicked at, and it gives me the X and Y pixel of the mouse click event. So if I click somewhere here in the default assignment, you can see left mouse button clicked at 325, 135. And so what you want to do is you're going to call spawn bullet, and the bullet is going to be spawned at the player's entity, and it's going to be given a vec2 target position of event.mousebutton.x and event.mousebutton.y. And so that's what you're going to call there. Excuse me, I got to take another drink. Similarly, when the right mouse button is clicked, that's when you fire the special weapon. Okay, that's it for the game class. I know it's a complex class, but you know, there's lots of commenting there. I'll put in some more comments for you before I release the assignment. So it may be tomorrow morning before the assignment is out, but that's okay. And the last thing that we have to do is the entity manager. And so none of that stuff will work until the entity manager is done. And you just have to implement the functionality that we talked about in the last set of slides on the entity manager. So right now, in my test code that I've given you, when you call add entity, it immediately sets up the shared pointer in the way that I described in the slides, but it immediately puts it into the vector of all entities. That's not what we're doing. We have to implement this function so that entities are added to the mEntities2add vector. Remember that buffer vector that we talked about last time? And then it's added to the actual vector in the update function. So entity2add is just going to add things to that buffer vector. Then in the update function, what we're going to do is we're going to take all the entities from that entities2add vector and add it to the proper location. So we're going to put them into the vector of all entities, and we're also going to put them into the entity map indexed by the entities tag. And also, we're going to clean up all of the dead entities from the vectors as well. So the pseudocode for that, again, was that for all entities, if not entity is active, I think it's is active or is alive? Yeah, is active, then remove E from the vectors, okay? So remember, you have to remove that from the vector of all entities, and you have to add it, or remove it from, let me just type it for you, okay? Because this is going to be a little bit tricky. So what you're going to do is you're going to say for auto E in M entities, so you're going through every entity, and you're saying if not E is active, right? This is the sign of a dead entity. This is the sign of an entity we want to remove. So we've tagged the entity as no longer being active, and we want to remove it. So what we do here is I've provided this helper function, which you want to implement, which is going to remove the dead entities from a given vector. So actually, that was the pseudocode for this function. So what you want to do is for auto E in vec, if this is not active, you want to remove, remove E from vec, right? And so I talked about that last time, how you remove things from vector. You can go look up the syntax of that in a vector. Or one suggestion that someone else had is instead of removing dead entities from a vector, create a second temporary vector of things that are just alive, loop through the vector, and then add those to the temporary vector and set that vector back. So however you remove the entities from the vector is up to you. But, oh my God, excuse me. You can use this helper function if you want in order to do that. So just remember that in the entity function, you have to remove dead entities from M entities, which is the vector of all the entities, and you have to also remove dead entities from their vectors in the map. Okay, so we've got entities that are indexed by the map. Excuse me. Right, so let me go back to the blackboard because this is a little bit confusing. Erase all this. Okay, so I just want to make sure that this is clear what you have to do. We've got a vector of this is all entities. And then down here, we have a map, right? And this map goes from tags to vectors of entities. So, entities are in our vector, and they have this Boolean inside them, which is true or false. So let's say that we have a bunch of them that are true, and then on one frame, one of these is set to false. Because we said, hey, a bullet collided with this enemy, and so I'm going to destroy it, and what destroying does is just set this equal to false. So then on the update function of the entity manager, I have to do two things. So let's say this was, oh God, this is green, and there we go. Let's say this was a bullet, okay? So we have to first remove it from the vector of all entities. But we have to also remove it from the vector corresponding to the bullet entry in the map. So the map down here will have some bullets in it, and one of them was this bullet that was false. And so we also have to iterate through the map and remove the entities in each of the vectors in the map that were dead as well. Okay, so that's probably going to be the trickiest part if you're new to the syntax of C++. And if you want a little hint, if you want to iterate through a map, here's one way to do that. So this is how we can, programming. How to iterate through a map in C++. So let's say we want to get access to all the vectors that are inside the map. We can say for auto reference KV, so KV is a key value pair, and this will be in the entity map. So the key value pair that we have, if I go back here, the key is the tag, right? And the value is the vector. So if we look at the definition of our map, the key is the first thing and the value is the second thing. So the key value pair, standard string, so the key kv.first, this is the tag. So this will be the tag. And kv.second, this will be the vector. Okay? So kv.first and kv.second, because maps actually implement standard pairs. So kv.first, the first thing is the key, which is the tag. kv.second, the second thing is the value, which is the vector. So you want to iterate over these vectors and remove the dead things from this vector as well. So, and that's all you have to do for the entity. Oh, one more thing is down here, you have to make sure that you return the correct vector from the map, okay? Yes, but yeah, so C++ 17 is allowed. There are other ways to iterate through that, but I'm just showing one of the more intuitive ways and the way that I know right now. Okay, and that is the assignment. And I know it looks like a mouthful, but it is. And so people who were complaining about not having enough to do on the first assignment, your wish has come true. You have enough to do on the second assignment now. But here's the thing. I don't want people in this course to fall so far behind that, say, if they miss the second assignment because of illness or emergency or whatever, that they won't be able to do assignment 3. And so for assignment 3, what I will be giving you is my working entity manager and my working vec2 class, okay? So you are doing this once and only once on the second assignment, and this will become part of the thing that I give you on the subsequent third and fourth assignments. So you just have to implement it once. You don't have to implement it every time, so don't worry about that. And you're going to have 2 weeks from today to do the assignment. I recommend getting started on this because you're going to run into some C++ syntax errors you've never seen before. You're starting to use the entity component system. You're starting to implement all that functionality. Some of your physics may have weird, like off by 1 errors. And so you may have, you may not be able to do this on the last day or two, right? Start pretty soon so that you can, if you have problems with the assignment, you can come to me with those problems. And again, I'm still cleaning up a little bit of this, and I want to give you more and more help in the comments in the assignment. So this is not up yet on the website, but by the time you wake up tomorrow morning, this will be there on the website. Okay. Oh, cool. So I just had a comment in the code, or sorry, in the chat, which said if we want to iterate through a map, we can do something a little bit more intuitive, like this. And I guess this is not the perfect syntax. So I'm not sure of the exact syntax of this, but a syntax exists which looks like this. Okay, so I forget what that feature of C++ 17 is called, but you can use that if you want. Also, when it comes to removing dead entities, there is a functionality that you can Google called standard remove if. Okay? Standard remove if has a strange syntax, but you can Google the syntax. And essentially what you can do is pass in a vector and a lambda function, And a lambda function I'm not going to get super into. So this is just an optimization you can do if you want. And the lambda function will evaluate itself on each element of the vector. And so if you pass in a lambda function, which says whether or not the entity is alive, then the C++17 standard remove if will remove all of the dead entities from the vector for you in linear time. And so that's something you can look up if you don't want to have to implement that by yourself, is just get your head around the standard remove if functionality. Or syntax, sorry. So that's assignment 2. It's a fun assignment. You'll start to see how powerful ECS is. Like, for example, if I wanted an enemy to live for a shorter amount of time, I can just change the lifespan in the config file. If I want the bullets to be bigger, I can just edit the config file. So this combination of entity component system, so ECS programming, and the data-driven design of having configuration files for everything is going to be really, really powerful and really, really fun going forward. But my throat is about to die. I'd love to sit and talk about this more because I absolutely love this kind of stuff. So thank you so much for tuning in today, and I hope you have fun with assignment 2. And always, as always, I'm available via Discord or email for questions. And thanks for watching. I will see you on Tuesday.